we have David Cano, that I hope is around. I cannot see him. Okay, I see him now. That is a postdoc research at the University of Pisa. And the idea was really to focus on some of the issue related to system dynamics that we discussed with Luis in particular this morning, and to try to understand how to make. So the idea is to have something that is a bit in parallel between the 4 days of the MOOC that allow us to build this kind of simplified integrated assessment model that I think at least at the end should share some of the future of the big integrated. So in the big William, of course, we have less than one. I mean, probably the scale is 1 to 1,000, or maybe more than that. So of course, many simplification are important. But however, I think that there is one issue that is something that you can use. And we ask also you to try to use this model for making some changing. So if you want to think about some policies or some changing scenario and parameters, so it's something that should have this degree of complexity or simplicity, if you want, able to work at the end of the course. Okay, so David, if you want, I give you the floor. So I will be here with you if you so if I can help.
Okay, thank you. Thank you, Simone. Hello, everyone. I'm trying to share my screen. Can you see my screen?
Yes.
Okay. Yes, so how Simone was saying, I'm going to start with this lab to try to build a simplified version of William. So the idea is to learn the basics of system dynamics modeling in Vensim. We're going to build a simple model that integrates economic, environmental, and demographic modules in a very simplified way. So this is part of the integration that William contains. And we are going to simulate some scenarios where different limits are reached, also to get in touch with the limits inside William. And then we are going to analyze the effects of policies and propose some alternative solutions in the project work that you are going to do. This is a bit the schedule of these labs. So today I'm going to focus on system dynamics and feedback loops, building an integrated assessment model from scratch, basically the climate change and population dynamics. The second day, you will see the ecological module, which models energy and materials limits. The third day, there will be the economic module with consumption, investment, and labor market dynamics. And the fourth day, the model will be already complete. So the idea will be to play with some policies to see the different scenarios. And then in the project work, the idea is that we also propose alternative policies. So, okay, this is from Vensim, but I think you already have it installed. So also, if you, I suggest to watch some tutorials of the software. And this is a bit sketch of the model that we're going to build today. So we're going to model output exogenously, and there are like 2 modules to arrive to climate change: the concentration of CO2 and the forests that absorb this concentration, and the concentration of CO2 generates climate change. And in red, I put here the arrows of the feedback loops. Climate change reduces output and also can reduce forests. So we will see what happens in different scenarios. Okay, so first, so I will open Vensim.
So this presentation is available on the drive. So if you want to download just to see the question, if you're curious, you will find that. I don't know if David is able to do both. Maybe yes.
Yes. I think it's better if you can follow also the presentation. I will jump between Vensim and the presentation, but the idea here is to see the equations and give a bit of explanation of what I'm going to do in the software. Okay, so this is the model already, but the first thing is to open a new model. So click on File and New Model, and here we can enter the settings of the model. Basically, to choose the units of time, I would choose a year. The initial time is usually 0 and final time 100. So we're going to simulate 100 years, and the time step is 1. Okay. And we have the first this white screen, which is the where we're going to work. This is called view, so I will call this view here down as climate change. Okay, and something important is to save the file. I will save it even if there is nothing yet already. Call it model 1. Okay. So the first thing that we're going to do is to model output. Output is a flow variable. This is the value of production or expenditure or income per year. And we're going to assume that it grows at 2% per year. So we're going to create a variable. And there are two types of variables. There is the stock tool and the variable tool. Since this is a flow variable, I will use the variable tool. You click here. Click any part of the view and just first write the name of the variable. Okay. And we can create also different variables that are going to be useful to model this. So in the presentation, I said like, okay, we will assume that GDP grows 2% a year. This is a linear rate of growth, not an exponential rate of growth. And we need some parameters, say some exogenous inputs to model this, mainly the initial level of output and the rate of growth. The time, we already have it. So I'm going to create also other variables for the initial level of output. I'll call initial output, and another variable for the rate of growth. Okay. So now we have the variables, but we can put these arrows. So you may click here in the arrow, and here we put the causal links that will go in the model. Now we have to put some information inside these variables. So we may click here in this tool that is the equation tool. It has the like a function sign. And when you click here, all the variables are in black because they are not defined. So I will start with initial output. It's the easiest. Here you see this is the window when you define a variable to write an equation. So here's the name. In type, I will choose initial because it's an initial value. It's also important to check the units of the variables. So I will put here euro. But since this is a flow variable, this will be euro per year because this is the amount of euros produced in a year. And I said that the initial value is going to be 10,000. So I just write 10,000. And that's it. Here at the bottom part, we can check syntax. This is very simple, but it's always useful to check the syntax of one variable. And okay, so we have already the initial output. Now the growth rate. This will be a constant. Okay, so constant. In units, I will put DM and L, which means like no units. This is a variable without units, but this is per year. And the rate of growth was 2%, so 0.02. It's check syntax, okay. Now we have the two parameters to start the modeling output. So now I'll write the equation of output. And this variable will be called an auxiliary. An auxiliary variable is like all the flow variables. So, and since you see, I put the two arrows from these initial values. So I have these two inputs here. So I can just select each input and it will start writing the equation. In this white space here is where we write the equations. So I put initial output times the asterisk, parentheses, 1 plus growth rate times time. Time is a variable that exists already in Vensim, so it's basically the time variable. And in units, I will put again here euro per year because this is a flow variable. Okay, so when I click check syntax, it says the following inputs were not expected but I use time, and it just asks if one wants to update the diagram and the input list. So I just say yes. Okay, and now we have output, and we can run this model. So the run name here in this part, you can change the name of this each run, each scenario that you're building. I will just write baseline and audio. And I will make click when it says run a single simulation, just to show you more or less what happens. Then we click the variable output, and here in the left, we click on graph, and it just shows the graph of output. Okay, so far this is very simple. We are going to start adding the other parts of the model. So the other part of the model was the CO2, the CO2 cycle. So as it was said in the presentation in the morning, the CO2 cycle is the CO2 concentration is a stock. So I will use the stock variable. I just write CO2. As you see, this is a box. So this is to differentiate the stocks from flow variables. And there are here, there is the flow tool in which we can put the inflows and the outflows for this stock. So I will click here to the left and click inside the box. And this is the inflow that I will call emissions. And then another flow, another flow that is an outflow. I may click inside the box and then I click to the right. And I will call this sequestration, the carbon sequestration. Okay. And we also need starting value for the stock of CO2. So I will add another variable that will be the initial CO2. Okay. So I have to add equations for all of these variables. In initial CO2, I will put 1000. And in units, I will put tons. This is also a constant, so check syntax, okay. And I will add a variable from CO2 to the stock of, for initial CO2 to the stock of CO2. Then something nice of Vensim is that if you click in the flow in a stock variable, you see that the equation is already there. It just takes emissions, which is the inflow, minus sequestration, which is the outflow. And here you can put the initial value. So here I will just put the initial CO2. And in units, I will put tons, which should be like the tons of CO2. And this type of variable, the stock is level, but it's automatically selected by Vensim. Check syntax, everything is okay. So good. I will go back to the presentation to show what we are going to do in CO2 concentration. So this is the result of two compensating flows, CO2 emissions and carbon sequestration. We'll assume that emissions depend on the level of output by a parameter alpha, which is the emissions intensity. And sequestration will depend in the stock of forests that we will model later. So we'll start by modeling the emissions. Okay, so I add another variable, which is this parameter that is emissions intensity. Okay, and here I will put 0.005. This is a constant, and the units are tons per euro. So how much tons are emitted per 1 euro of output? Check syntax, okay. And now I add the two arrows from emissions intensity to emissions, and from output to emissions, which are the two determinants of emissions. And now I just write the equation of emissions, which is just the multiplication of these two variables, the emissions intensity times output. And in units, this is important also, as it was for output, all flows variables are per unit of time. So I write tons per year. Okay, and now in sequestration, I will just write 0 for the time, just to see what happens in the model. So I will run again this. And we can see that emissions follows also linearly from output. Okay, now we are going to model the forest. So forest dynamics is also very simple. It's like a Stoke dynamic. So it's the result of reforestation minus deforestation. So I will do the same here. Add a stock variable that I will call forest. I put the inflow and outflow. I will call this regeneration, in the sense that this is like a natural, the regeneration of the forest. And the outflow would be deforestation. Okay, I also need to add the initial level of forest. Okay. Okay, so I have to add the equations now to forests. The initial forest, I will assume that is 30,000. And the units of these are hectares, so the hectares of land covered by forest. Okay. And now for regeneration, we are going to introduce a bit kind of more complex function. So this is also to answer the question in the morning of what happened with the dynamic equations inside this model. You put all these equations inside the variables. So the regeneration would be basically a logistic growth rate, which is this, like a maximum forest regeneration rate multiplied by this, which is basically the percentage difference between the carrying capacity of forest and the stock of forest, and this multiplied by the stock of forest in the previous period. So we have here two parameters: the maximum forest regeneration rate, which is 5%, and the forest carrying capacity, which we'll assume that is 50,000 hectares. So there is a degree of deforestation at the beginning. Okay, maximum regeneration rate. And here I will put the forest carrying capacity. Okay, so in maximum generation rate, I will write 0.03. This is a constant. The units are no units, the rates of growth, we don't have units, but this is per year. So this is the change per year, basically. And check syntax, okay. And now in forest carrying capacity, I will put 50,000. This is also a constant, and the units are hectares. Okay, and now I add the two arrows. And then I write the equation for regeneration. I will go back to see it. Okay, so it was the regeneration rate times the percentage change times the initial stock. So, oh wait, I have to put an arrow from the stock of forest so I can write the equation easily. So this is the maximum generation rate multiplied by, it was, okay, 1 minus the stock of forest. So I just click forest here. This stock is usually the stock from the previous year or the previous period. The stock of forest divided by forest carrying capacity, and this then multiplied by the stock of forest again. And the units are, again, since this is a flow, these are hectares per year. So the amount of hectares that are recovered by forest each year. Okay. And now I will add the equation for deforestation, which will assume that it's just affected by output with a parameter 0.03. So I will add this parameter, deforestation intensity. I will add the value, which is 0.03. The units are hectares per euro, so the same, like how many hectares are deforested per unit of output. Good. And okay, now I'll put an arrow from output and an arrow from deforestation intensity to add the equation for deforestation, which would be, yes, deforestation intensity times output. And the units are again hectares per year because this is a flow variable. So the amount of hectares that are lost each year. Oh, okay, so now I am missing the equation of forest. Okay, so in forest, I was missing only the initial value, which is initial forest, okay? And the units are hectares because this is a stock. And now I will add the feedback from forest to CO2. So this is the feedback of the fact that forest, oh no, wait. The feedback is from the stock of forest. Oh, so the fact that the stock of forest help to absorb CO2 emissions. And I will need to add another parameter, which is the carbon sequestration rate. Okay, and this will be 0.0025. And the units of this are a bit strange, but it's just tons per hectares per year, because this is a flow variable. So it will be important to put years. I mean, this is not a flow variable, this is a parameter, but this is per year anyway. Okay. So now I put another arrow. I should be able to delete this arrow here. Okay. Okay, here we have two delete tools. Be careful with this and later, because one tool is to delete something forever from all the model, and the other is to delete only from one view, because you can put variables from another view in this view, but this is not happening now. But just in case, be careful between these two delete tools. And now I will write the sequestration variable. Now it's not longer 0. This is the carbon sequestration rate multiplied by the stock of forest. and the units of these are tons of CO2 per year. Okay, so now we can see what happens with this model. I will put this forest, because now we have the effect of forests, and I will run a new simulation. And now we see the concentration of CO2 is much lower with forests. Now, when we don't have the absorption of forest, the CO2 concentration grows along with output. Now it grows less, and it even reduces a bit at the beginning. Okay, so this is the first part of the model. I have seen a lot of comments in the chat, but I cannot see them. So I would like to receive some feedback of the people, because also it's close to 1 p.m. We still have to model all the climate change part. So I'd like to know if we have time for this, or
yeah, I think let's do it this way. I think we can go on, but just to, if you want to take a couple of comments, if there is something that is unclear, or so most of the, so it was quite funny because you answered to many questions inside the group. That is great. So,
okay.
But I don't know if there is something that is still missing. Otherwise, we finish in almost 10 minutes. So I mean, there are a few questions that are missing.
Yeah, so there is a question about if output should be exponential, and yes, we can make an exponential rate of growth, but we just made it linear, just because there is no particular reason. But it's easier here to work with the units, basically.
So remember, what is important is that now we are taking output exogenous. It will not be exogenous at the end. I mean, so we will see that the effect will be different.
Yes. Yes. So we are modeling the output is exogenous. There is a question of how do you make the time icon appear? So it's I just when I modeled the equation for output, I just put time inside the equation, and it gave me a message of you want to add this to the diagram. I click yes, so it just appeared automatically. I mean,
yeah, okay. This is a difference between the full version that David is using and the PLE version. In the PLE version, you have to make the shadow variable. So click the shadow variable and say time. That is one of the variables that is set by the model itself. Okay, it's clear the difference. So if you have the PLE version, you have to click the shadow variable, just show that is the ones between the two, and write time, and of course you can introduce the time variable. Okay.
Yes.
So
and there is another question of how to plot the two different scenarios. This is each time you make a run, it stays in memory. So since I do 2 runs of the model, it automatically shows the 2 scenarios. The output is the same. This is why we see only a line. But in the stock of CO2, they are different. So if I run another simulation, it will stay there again. But I will show you later how to add or how to include or not some runs in the graphics.
Okay, I think let's move on, and then maybe we collect some questions also on the lab for Monday.
Yeah. Okay, so we'll go fast to the climate change part. So this is a bit complicated, but I will do it fast. So climate change, we will assume that basically emissions have an effect on temperature, and temperature increases. We'll use a normal distribution with this mean. So 25 degrees is like the base temperature, plus 2 multiplied by the percentage change in emissions. Oh, okay, so I will just add a variable called temperature. From CO2 concentration to temperature. Okay. I will click here, and here I will put here you can select the functions. So we'll select the function which is random normal, and you see it shows you the parameters that we should put, the minimum, the maximum. So it kind of truncates the functions. The mean, which is the function I just showed, and standard deviation at the seed that just determines. You can change the seed and you will have different values. So in minimum I will put 25. In maximum I will put 100. I could also do this putting different variables which are the minimum and the maximum temperatures, but I will do it here to do it faster. And the mean was 25, which is the base temperature, plus 2 multiplied by the change in temperature, which is CO2 divided by the initial value of CO2 that I can put it here as the variable, but I will just write the number 1000 minus 1. And in standard deviation, I will put 0.5 and seed 10. And this equation is okay. Okay, and now I'll put the damage. The climate damage will be simply, I have to put a new variable which is called damage, which will be simply the percentage change in temperature from the base, which is 25. So this will be just the temperature minus 25 divided by 100. Okay. I will write another run, which I call climate change. Yes, climate change, just to show you the damage. This is and the temperature works like this. It actually increases a lot. It arrives until 35 degrees, so more than 8 degrees by 10 years. But okay, we can change the parameters and have different effects. Good. So now the important thing is the feedback loops. First, we will assume that there is a feedback loop from damage to output. So we will assume that damage somehow affects output, and I will add a parameter which is the output sensitivity to climate change. So this just be just a parameter that we can alter to simulate the sensitivity. Yes, to simulate the more stronger or weaker effects of climate change on output. And there are also different ways in which we can model this effect of damage. So a good experiment will be to change this parameter or to change the effect in which damage affects output. So I will put output sensitivity to climate change multiplied by damage. So basically, the rate of growth is reduced by this parameter multiplied by damage. Okay. So let's run the model. I will call this damage Y, which is output. Oh, I have to put also the value of the parameter output sensitivity. I will put 10. Okay. So now let's see what happens. I will run this. Okay, we have this run. So I will show you how to put more or different runs in the graphs. Here there is this tool which is called the control panel window, and here you have the data sets. Each run is a different data set. So each time you make a run of the model, it creates a new data set. So I will take a forest and climate change, which were like intermediate runs that I made, and we'll have only baseline and damage on output, and see what happens with output.
Read, there are many questions because we were going a bit faster. So, but
yeah.
maybe could you open again? So, okay, just comment this and maybe again show the temperature equation that.
Okay.
So maybe you can find the file, this file on the drive already inside the folder lab.
Yes, in the presentation you can see all of that. I will explain again the equation, but first I will talk about this output. So okay, we have that without damage, nothing happens. With damage, the output decreases. But an important thing, an interesting thing is that with damage also the CO2 emissions are a bit lower, and they are lower because with damage we have a lower output, and this lower output has an effect on deforestation, right? We have also, okay, I don't have the baseline for deforestation because I run it before, but you see that deforestation also starts to reduce because of climate change. So there is kind of a feedback in which climate change reduces output, but output reduces deforestation, and this more or less mitigates the CO2 concentration.
David, just to show, since the only feedback is the one from damage to output, if you put 0 on the output sensitivity to climate change, you come back to the baseline, no? So just to show you them how to do it.
We can do
so
this.
If you enter in the output sensitivity,
yeah, I can put here 0. So I will not have.
So remember, for do the baseline, is important that here you write baseline in the same way. The run name you have to write down.
You have to have the full model before having a baseline. But I will now also run the baseline again. Good, and we can see deforestation. Yeah, so without climate change, deforestation was much higher. Okay, so maybe I can answer some questions. So there was a question
maybe,
about...
David, just put again the value if you want to go on, otherwise we forget for sure.
Yes. Okay, 10. Good. Okay, so I will see the questions in the chat. A lot of questions.
Okay. I mean, I think that there are a lot of good answers. There are something that is not clear yet.
Yes, so the
okay,
data files...
so of course, some of the assumptions are really strong, no? Someone says... okay, no, it's not smooth just because so we try to consider this kind of random variable. So it's a random process that changes the temperature, no?
Yes. A question about the data files. They are generated by the model. They are generated. Yes. I mean, this is the data of the simulations. So if you go to the folder where I save the model, each run generates a new file, which is .vdfx, and these are the data sets of each run. This the data set for inputs or for calibration is another thing, but we're not going to talk about that. Which other questions?
Okay, if you go back to Vensim, just to show that you can represent the result also with data. So there is the table where you can look at the...
yes, you can also, for example, click in CO2 and you can see the graph here, or you can see the table and you have the numbers. So this is actually the data sets that each run creates. So each data set is this, like one value per each time step for all the variables that there is in the model. Okay, so I think that maybe we can leave this here, or maybe we have time to add another feedback. What do you think, Simone?
Yeah, I mean, the last one, I don't know, the last link, just do it, okay. And then,
yes, we can have another feedback which goes to damage to the regeneration. So to assume that climate damage also lowers the natural regeneration of forests. We can add another parameter, which be regeneration sensitivity to climate change. And I will put this in 4,000, which means like 4,000 hectares less per each 1% increase in temperature. And I will model it just like this, just put in minus regeneration sensitivity to climate change times damage. Okay. And we create a new scenario. I will call it damage YF, so damage on output and damage on forests. And see what happens to output. So it's a bit lower, say that with damage on forest. And the CO2 emissions also are a bit higher now. So in the baseline, they were high. With damage only on output, they were lower because of the effect of output on deforestation. But if we add an effect of climate change on the regeneration of forests, the emissions will increase a bit, and this will create other feedbacks. And okay, I think we can stop here.
Yeah.
It was
okay. Thanks a lot, David. I think was nice to follow. Was excellent. A bit faster, but we had a few minutes. So
yeah.
whatever, if you want, there is a few. So we have some minutes to answer to some questions. If you have some comments, also if it seems so too difficult to follow or too easy, I don't know. Even for next labs.
There is a question here. Isn't there also a causal loop reducing emissions with lower output rather than only the effect of reduced deforestation? And yes, this is kind of automatically because emissions also depend on output. So also, of course, also lower output will reduce emissions. Yes, it was a bit too fast. I'm sorry, but we thought that this model was already small, and even if it's a small model, it's not that small. But okay, thank you for your attention. I don't know if you have more questions. Okay, about the equation linking CO2 to temperature, I think yes, this is a standard way of modeling climate damage. I don't know if you can answer better this, Simone.
Okay, I mean, this is some typical, very simplified way of connecting CO2 to temperature. Of course, was just an example. So don't take these numbers as reasonable or not. So my idea is that, of course, there is an increase in temperature that can follow this kind of dice model. But so it was really a very strong simplification for getting also this. I mean, to show this normal distribution that is maybe nice, not to see that we can work with the seeds. So for instance, maybe one thing that you cannot do with PLE version, but we can do here that maybe is nice, is to see the sensitivity, no? So we can play with the sensitivity of the seeds to see which is the kind of divergence that you can have in changing the random, so the random process that we fix with the seed inside the normal distribution. Okay, so whatever J. Christopher was not really a reason, was just an example.
Yeah, just an increasing function of CO2 concentration, and then random normal to make it kind of random. I mean, stochastic.
But I'm pretty sure that most of you has a better function. So if you want to change and send us back, please, it would be great. Huh?
Yes. So in the drive there is the model, and also there is a presentation. In the presentation, I also was expecting to add the population, but maybe you can do it by yourselves to add like a population dynamics. And the idea will be to keep completing this model in the next session. So thank you very much.
Oh, no, of course I will do. So the video and the recording will be uploaded today. for sure. Okay.
Okay.
And so Vensim, so we try to explain with Luis. So there is a version that is the PLE version that is free, while the more, I mean, full version are not free. And so whatever the link that we share, there is the version that you can download with the one that we can work together. At the same time, Luis Javier was suggesting that there is also a reader that can be used to open more complex model that has vector. That is the main, I mean, limitation of this PLE version.